Welcome to Spring LIB.
Alrighty, so we have this long flat straightaway that the animal is running on, and then we have descent into the desert below, and this is a certain height that we have, 100 meters, and of course we have some sort of initial velocity here, and that's going to be all horizontal at the beginning, falling off the cliff, or you're flying off the cliff. And we have quite a bit of stuff for me to figure out here. I'm going to create a little bit more space here for myself. I know the motion falls off here and stuff, but let's just to save the space, let's cool, there you go, really quick fall. All right, box that in. All right, there's our little schematic of what's going on. First thing I want to do is I want to get the time it takes for the coyote, or this animal in general, to get from here to the edge of the cliff. So I'm going to use my kinematic equations. Let's start with this one here. X final equals X initial, and this is equal to plus velocity initial times the time, and plus any sort of acceleration here. So we have plus 1/2 acceleration in the X direction times time. And see, I'm breaking this problem down two problems here. I have just this motion right now that I'm analyzing. I haven't even gotten off the cliff yet. I'm just right up to the edge of the cliff. Now, this X final and X initial I can set at 0, and I know that this total distance here from where the cliff is will then be 70 meters. So I'll put 70 in here. And this is 0, because the X initial is at 0, and there is no initial velocity. We start at 0, but we have our 1/2 multiplied by our acceleration, which is 15 meters per second squared, times time squared. And then here I could solve for time real quick, which is convenient. When I do that, I get time equal to 3.06 seconds just by isolating t by itself and taking the square root. 3.06 seconds. That's how long it takes with these parameters. 70 meters at an acceleration of 15 meters per second squared. It takes me 3.06 seconds to do that acceleration, and then I can find the velocity here by just using my simple kinematics. Then velocity just being the position over time, which would be 70 divided by 3.06 meters or seconds. And then when I do this, we are looking at velocity in the X direction equal to 22.9 meters per second. All right, so now we want to figure out the velocity So we just figured out the time it took, and then we found the minimum speed of, this is actually the speed of the other animal, not the coyote. I'm sorry, just to be clear here. This is the velocity of the roadrunner. I'm going to write it right here, roadrunner. And the other animal is the coyote, and we're going to do that information next, which we can simply use the same information that we have from here, at least similar information. If I just split this up right here, we're going to do velocity final, and this is now going to be for the coyote. And we have velocity initial of the coyote plus the acceleration times the time it takes. So we want to do this in the same amount of time that the roadrunner is doing it in. So velocity final is going to be equal to, we have no initial velocity, that is 0. So it'll be equal to just the acceleration times the time. So acceleration times the time, 3.06 seconds, same acceleration. And then we get a velocity final of 45.8. Cool, box that in. Now we're going to do the second part of this problem here. So we have the part where this motion now, you go to the ground here. So we have to figure out the second part of the motion, which we'll analyze now. So one thing we do know is we just found the initial velocity from the first part of the problem here. We have this v initial. And that's what I mean is it's the part right before it falls off the cliff now, in the second part of the equation. In other words, the final velocity in part 1 becomes the initial velocity in part 2, which is the 45.8 meters per second. So we know that this is also in the x direction. There is going to be no initial velocity in the y direction at all. That's going to be 0. So we have that initial velocity. What we want to do now is figure out the time it takes to get to the bottom. So what we're going to do is use our kinematic equation, very similar to the one that we used earlier here. We're just going to use it for a different part of the motion. My initial plus the velocity initial in the y direction times time plus 1/2 acceleration in the y direction times t squared. This y initial, we're going to set it at 0. We're going to say that this is the top of our, or the start of our motion here, 0. And the y final is 100 meters, since we traveled 100 meters in the y direction. Now this velocity here, there's no initial velocity in the y direction, so that's going to 0. And you have 1/2 plus 1/2 g t squared. And now we can go ahead and find time. By going ahead and solving for this, we get t equals 4.52 seconds. Now for the horizontal motion, we substitute the time that we calculated right now, and we substitute that into the kinematic equation for distance here. So that's not too bad. We're going to do that real quick. We can define this as d, distance. Using pretty much the same equation here, we're going to set that first initial as position, the x sub I, as 0. And then we have a velocity times time, which is the 45.8 that we got here. And I'm really using the same equation, guys, that I've been using pretty much this whole time, just in case you guys are confused on which one I'm using here. The x initial is 0 because we are defining the beginning of our motion up here at 0. We move a certain distance, so that's 0, and we want to know what this total distance is. That's why we have d there. And then my v initial is 45.8 times time, which for us, we're going to use the time that we just found, which is that 4.52 seconds. All right, and then we have an acceleration that's going on as well. It doesn't stop while we're in midair. We keep going with the acceleration that's described in the problem. So we have the 1/2 times the acceleration that we're using here, which is 15 meters per second squared, times 4.52 squared times squared. And then when you do this, we can figure out our horizontal distance during the projectile motion part of the problem. And that's 360 meters. That's this distance here from where it comes off the cliff horizontally to where it lands, 360 meters. All right, now for the vertical motion, we're going to go ahead and I'm going to make some space on this left side here, or right side rather. To do this, we can do this right here. Ooh, I don't want to cross that out. There we go. We're going to go ahead and use this very fancy and convenient kinematic equation, this v final in the y direction squared equals the v final in the the v initial in the y direction squared plus 2a acceleration in the y direction times delta y. All right. And what we want to do is solve for that final velocity. So we'll do that real quick here. We have quite a bit of information here already. We'll leave this guy alone. V final y squared. And then we're going to go ahead and We have no initial velocity in the y direction. That goes to 0 because all of our initial velocity is horizontal. There's nothing in vertical at the beginning. And then we have 2 times our acceleration downward, which is 9.8. It's working with us, so I'm not using a negative sign here. We're moving along the direction of where the gravitational field is pointing. And I'm going to put my 100 in here for my delta y. That's this distance of the vertical height, 100. And then I can square both sides of this. And then I get v final in the y direction equal to 44.3, technically negative 44.3 seconds if you, depending on how you have your axis system set up. I guess you could say it is pointing downward. If your y-axis, your positive y-axis points up. But it really depends on how you set up your axis. For the horizontal motion, we want to substitute the given values into the kinematic equation for the horizontal motion to find the horizontal component. And we'll do that as follows. And we'll just do that right down here. We don't need too much space for this last part. It's velocity x in the y direction, in the x direction, final. And that equals Vx initial plus acceleration in the x direction times time. Normally this would stay the same for a problem like this, but it's a little bit different in this case because we do have that acceleration while we're actually in flight. All right, so we have 45.8 plus the 15 times the 4.52. When you do that, you will get 113.6 meters per second.